chapter 8. It's an intro to random variables, and this is not going to be in the test and is not due this Sunday, but we're going to cover it anyway. And if you have time, I strongly suggest that you get it done. That means you have less homework next time. So I'm going to introduce some terms that you've seen before. We have a thing called a sample space, which basically is a list, oops, funny F, of all the things that could happen. And now we're going to look at a new guy called the probability distribution. Essentially, what a probability distribution, it's usually in the form of a table, is that you write down on the top all the things that could happen, and then underneath it, the probability of them happening. So let's create a story where we could do that. First one I'm going to do is the 3 children one, because it's pretty easy to do that for. Right, in the 3 children story, you can be a boy or a girl. The sample space essentially is every possible 3 children family that you could get. So in no particular reason, 3 boys first. Then you could have 2 boys with a girl, a boy, a girl, a boy, and a girl, a boy, and a boy. And then you could have a boy with 2 girls, and then it could be that the boy was the middle child, or it could be that the boy that you had was the last child that you had, and then you finish with all the girls. Now, it's a good idea when you're writing down sample spaces that you have some kind of systematic way of doing it. Have you noticed that the way I did it was all the boys, all the ways of getting 2 boys, all the ways of getting 1 boy, and then essentially all the ways of getting no boys, right, which was 3 girls. Now, by doing that, can you see there's 8 of them? And I know I've got them all. If I just randomly start writing down 3 children families, you know, like boy, girl, boy, 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 girl, 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 I'll get quite a lot of them done. But can you imagine what's going to happen when you get towards the end? You might not be able to find them all because you think you've got them, but there's combinations out there you don't know. And secondly, you won't be 100% sure that you've got them all. Couldn't you write down 7 and think you're finished? Because that's it, that's all I can think of. So try and have whatever systematic way you can come up with, try and find a systematic way of writing them down. Now, what a sample space would do is that you would have a variable called x. Its fancy name is a random variable. And we typically use x because we like x in math in general. And this random variable is something to do with the sample space. In this case, let's say it's the number of boys in the family. And then you create the probability distribution using your sample space. So it might look something like this: X, number of boys. And the book does it like this. I'm not really sure I like this, but I'll write it down. They write it like that. I would probably just call this the probability that you get X boys. To me, that would be a better way of saying it, but that's how they're writing it. So you look at this thing and you say, okay, then what could happen? Well, I could have 0 boys. I could have 1 boy. I could have 2 boys in the family, and would you agree I could have 3? And that's it. That's all you can get out of a 3-child family, from 0 to 3 boys. And then you make an assumption, which we will make, is that every single one of these 8 things, right? Every single one of these 8 things is equally likely. That might not be a valid assumption in every situation, but for the sake of these questions, we typically make that assumption. And if I want to do 0 boys, basically doesn't that mean 0 boys because they're all girls? And how many times does that happen? It happens 1 out of 8 because there's 8 things here in the sample space. Now, if you're looking at 1 boy, it can happen 3 ways. And if you want 2 boys, it can happen 3 ways. And if you want nothing but boys, 3 boys, that can happen. What am I putting 0? Yeah, sorry. 0, 1, 2, 3. And that can happen 1 way. And this is called a probability distribution. And it has a number of features that all probability distributions should have. And here's one of the most important properties. What should all 4 probabilities in this table always add up to in every probability distribution world? Agreed. So if it don't add up to 1, right, you've probably screwed up somewhere, right? Now, from this table, you can answer other questions. I could, for instance, answer a question like this. Suppose I choose a family at random. Oops, here we go. What's the probability that there are more boys than girls? Well, you look at your table and you say, okay, what does more boys than girls mean? Would you agree that it means 3 boys and 2 boys? Wouldn't those 2 be having more boys than girls in this story? And what does that add up to? Well, it adds up to 3/8 plus another 1/8, which is 4/8, which ends up being a half. Okay, so half the time, there are going to be more boys than girls in the family. And I bet you the other half of the time, isn't there going to be more girls in the family than boys? And it kind of makes sense when you think about it. Now, so far, so good? Now, suppose I went and said to you, what's the probability that there were no girls? That would be the same as all boys. Agreed? In which case the answer would be an 8. So sometimes they might phrase it in a way you have to think a little bit about it, but hopefully not too much. Now, back to the sample space. When it was a 3-child family, there were 8 things in the sample space, right? It would be nice, wouldn't it, if we could figure out how many things are in the sample space so that we know when we found them all and we can stop looking, right? So let me show you what is a very common method. It's the counting method. And what you do is you say, first child, second child, third child. And you say, there are 2 possible things that could happen for your first child, boy or girl. You multiply it by the 2 ways that you could get your second child, and you multiply it by the 2 ways that you could get your third child, and you see how we now know there's 8 things that can happen in this particular sample space. Does that make sense? So if you do a sample space and you know there should be 8, but somehow or other you've only got 6, don't you just have to figure out who the other 2 guys are? Now, if you do it systematically, it probably won't happen, but you know, sometimes you do it systematically and still you miss somebody because you're just a bit careless or whatever. Suppose I wanted to do a rather difficult question and I don't want to make the entire sample space. Can you imagine the sample space could be huge? So I'm going to do one. Suppose I did a 7-child family. Now, you trust me, you do not want to do all the sample space for a 7-child family. Wouldn't that be the end of this period? Probably by the time you've wrote it down. But I still want to know some probabilities from it. Not necessarily this one, but it could be. Suppose I wanted to know, what's the probability that every single one of them is a boy? 1, 2, 3, 4, 5, 6, 7. In other words, I wanted to know that from the first child to the 7th child, everybody was a boy. Now, I only need to know 2 numbers. The first number in this story is easy. It's going to be 1. Agreed? Won't the bottom number be the total number of things in the sample space? But I don't want to write them down. But can't I use the counting method? If there are 7 children in the family, won't the total number in the sample space be essentially 2 times 2 times 2 times 2, that times 2? Won't it be quicker in math just to say 2 to the power of 7? And that's why you have calculators. So 2 to the power of 7 is 128. So I now know that my probability of having 7 boys in the family is 101 out of 128, which I'm now going to turn into a decimal, which is 0.0078 roughly. And now I'm going to turn into percent, 0.78%.
Professor?
Yes.
Melissa just emailed me and she says that she's in the waiting room right now.
Thank you for telling me. I've just made her let her in. Thank you.
Right. Mm-hmm.
God, you lot are good. It's not that I've trained you because you figured out how to help me. Yes, this is good. Have you also noticed that you tell me when I do things wrong, which I honestly do like, because it means you're paying attention and, you know, oops, that shouldn't be a 4. I like that as well. So thank you. There is, and I can't remember the darn story, so this is slightly wrong, but there was a family in America that had 13 boys. Right? 13 children, and every one of them is boys. That's going to be 1 out of essentially 2 to the power of 13. Can you see where the 2 to the power of 13 is coming from? Isn't that the total number of things in my sample space? So I don't need to write them all down. It's going to be ridiculous, of course. It's 1 out of 8192, which I'll just turn into a percentage now. It's about 0.01%. And that isn't 0.01% of American families will have 13 boys. That's 0.01% of families with 13 kids in them. So there's not many families in America, I'm assuming, right, with 13 kids, right? Exactly 13 kids. And if you went to every single one of them that there are, only 0.01% of them would all be boys. So do you know the chances are there's only probably 1 family in America that fits that particular combination. True story about one of my family, my sister Morag. My sister Morag wanted a girl. You know, some mothers don't care a darn, right? If it's healthy, and all mothers want their kids to be healthy, but she wanted a girl. And she got a boy, which is what you'd expect sometimes, right? But what she got was 4 boys. Not 1 girl, 4 boys. After the 4th kid, okay, just give up, right? And so she gave up. And all of her boys, she's got 4 boys, right? All of her boys, oh no, I'll take that back. 3 of her 4 boys had have children, and 3 of the 4 had girls. And She's now a grandmother, and one of those girls is now married and has her own new baby, and it's a girl. So she couldn't have a girl to save herself, but she's got tons of girls as grandchildren and one great-grandchild. It just shows you the way probability can play tricks on you. I'm just curious, David, does your family have any weird combinations, like you've got an uncle with 6 girls in it?
No, everything's pretty mixed. I mean,
yeah, that's
I
a
don't
normal family.
yeah.
Yeah, that's normal. When you ask people, nah, but there might be somebody here that says, you're right, my Aunt Janice has got 4 girls or whatever. Now that does happen, but it happens quite rarely.
My mom.
So are we comfortable? Sorry?
My mom has 5 brothers and wanted a sister, and so she had 5 daughters.
Oh God! Right. So there's the other end of the coin, right? Where you can get quite extreme values, but probability just says this is the chance of it happening. It doesn't mean it won't happen. It just means it's unlikely, and that in itself is fine. Okay, are we cool about creating sample spaces and making these new guys probability distributions, and that you can use counting methods to find specific probabilities without having to resort to one of these? And you would, I would say, in practice, if somebody gave you this question, and definitely if they gave you this question, wouldn't you basically just do the counting method? Now, I'm just looking at a question that they've got here, and this one here is a very interesting sample space. So this is question 7. And a woman decides to have children until she has her first boy. Right? So she's going to have children until she has her first boy. And we are going to create the probability distribution for what could happen, right, in this situation. Like my sister who wanted a girl, this one is wanting a boy. So the sample space does not look like this. This is a special subgroup of families, right? So in this world, the minute you have a boy, the family stops growing, right? So there's going to be different number of children, in these worlds. For instance, she has her child and it's a boy. That's the end of her family. She got the boy she wanted, she's having no more kids. She has a girl first, and then she has a boy. And I've just turned this story back to front. No, I haven't. I take it back. It's the right way around. What would the next situation be?
Girl, girl, boy.
Right. Okay. And we'll do just one more. Now, what makes this sample space a little bit different is that she's only going to do it up to 4 children. So there is a restriction. I'm going to keep doing it until I get a boy, right? And I'm only going to do up to 4 children. So would you agree that's one way she will stop? That's the second way she will stop. That's the third way she will stop. And that's definitely the fourth way. But there is one more ... that fits in here. What is the last thing in her sample space that I haven't written down yet? She's still going to stop.
4 girls.
4 girls. So do you see that you have to be really quite careful when you read the story, right? The restrictions on what's she going to do. Now, each one of these guys is not equally likely. So we're going to have to factor that in to my probability distribution. So my probability distribution is going to be X. And in my case, X is going to be the number in the family. and then the probability that that is what you get. So what's the probability that our family only has one child in it? What's the probability it's got 2 children in it? What's the probability it's got 3? And lastly, what's the probability it's got 4? Would you agree that having a boy is going to happen half the time? So the probability of this one is a half. Now let's look at a 2-children family, totally isolated from the story, because that helps. The probability that you get a girl and then a boy. Well, in a 2-children family, isn't it 4 things that can happen, right? 2 times 2 is 4. And this is a specific order, girl then boy, so that counts as 1 out of 4. You see how I figured that out as a quarter? So I'm going to put this guy in as a quarter. Now, what about girl, boy? Well, if we think about what that looks like, it's a very specific order, girl, boy, so that's only going to happen 1. What's the bottom number for a girl, boy going to be? Use the counting method. 2, 2, and 2 more. 8. Agreed? 2 times 2 times 2. 2 cubed. 8. So that makes this 1/8. And this is just a little bit different, but not much. Since there are 4 things happening, would you agree that the bottom is a 16th? And that one and that one makes it 2. So the last one combined, that will happen about 1 out of 8 times. Are we comfortable about how we created the sample space and now the probabilities of it? Now, all I'm doing to finish this part of the question is, because they wanted it to be, I'm turning them into decimals. If I have created this table correctly, shouldn't these add up to 1? Boom, 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 boom. Isn't that a good check that I have created the probability distribution table correctly? Right, I've got the right answer. If that had added up to 1.25 or 0.9, wouldn't that be a good indication that I've screwed up somewhere? Any questions about that one? It's quite a good question because it just shows you that not all sample spaces are the same, right? They're not right down everybody. You know, this story here had a kind of different twist to it. Last chance, any questions or are we good? Okay, that seemed to went well. What we should do this time? Okay, this one is a class, and in this class there are, let's see what there is. There are 5 left-handed people and 15 right-handed people. So basically this is a class with 20 people in it, right? And in this class, you're going to choose 2 people, right? Right, at random, I'm picking you, Cheyenne, and you, David, right? Whatever it might be. We are going to look at creating the sample space for choosing 2 people. How about left, left, a left, right, a right, left, and lastly, a right, right. Would you agree that those are the only 4 things that could happen when you choose 2 people and you're counting left and right-handedness, right? Both of them are left, both of them are right. Well, the first one was left-handed and the second was right. Well, the first was right-handed and the second was left. Right? So far, so good. Now we are going to create a probability distribution And in this probability distribution, we are counting, which is it? Well, let's count the right-handed then, right? X is the number who are right-handed. And then the probability that you get that. So there might be nobody who's right-handed, one out of the two is right-handed, or both of them are right-handed. So the probability distribution just has three outcomes, right? In my little thing up here, since we're counting right-handed, won't that be 0? Won't those count as one right-handed, and won't this situation here count as 2? Now, in this question, these 4 possibilities are not equally likely. So I can't just say 184, 284, 184. That would be good for boy-girl story. Aren't there less left-handed and more right-handed? So that means getting 2 left-handed people is not the same as getting 2 right-handed, right? So that means that these probabilities are going to have to be calculated. And once we know what they are, we'll put them in here and here, right? And the way that we're going to do it is by a guy that we've already met before, and that is the tree diagram. Right, so we actually have to do quite a lot of work just to find these probabilities. So I'll start off and I'll do the first pick. So the first person I pick could be left-handed, or they could be right-handed. Now, when you're choosing the first person, isn't there 20 people to pick, right? And 5 of them are left-handed, so 5 out of 20. And 15 are right-handed, and that's 15 out of 20. And I know I could simplify those fractions, but I'm not going to bother. It's not that helpful. Now, in this story, you have a second pick as well, right? You're picking 2 people. So what would the second pick be? Well, you could pick another left-handed, or they might be right-handed the next time. Or in this case, it could be another left-handed or another right-handed. But these are going to be, well, distorted is not a good word, are going to be altered because of what's already happened. You recognize that when you do a tree diagram and you get to the second pick, aren't you already knowing that there's a left-handed person already out there, right? They're standing at the side next to you. So what does that mean? It means that my probability of getting another left-handed person is going to be affected by what happened in the first pick. Now, if the first pick is left-handed, that means there's only 4 left-handed people and there's only 19 people left to pick from. Do you see where that 4/19 is coming from? Now, on the other hand, if you're picking a right-handed person, there's still 15 of them, but you're only going to pick out a choice of 19. Have you noticed that they 2 add up to 1? They're just split differently. Now, if you go to the second situation, a right-handed person came out first. So that means you've now got 5 left-handed, but 19 people to pick from. Since a right-handed person has been chosen here, that means there's only 14 of them out of 19. And then you get to the destination, which is these 4 guys at the end. Because once I know these, won't I be able to then go back and associate probabilities to these events? So for instance, if you want to know what a left and another left is, that would essentially be 2 left-handed, agree? When you do tree diagrams, don't you multiply the pathways? This probability times this one. So you're going to do, I think I'll turn into blue again. You're going to do it as 5/20 times 4/19, and that's 20 out of 380. And yes, I could simplify that, but right now I'm not going to bother because I'm running out of room. If I did this one here, that would be a left and then a right. And that would be 5/20 and 15/19, which get me 65/3. If I did this one, it'd be right and then a left, and that would be 15/20 times 5/19. Nobody noticed my mistake, or at least you didn't tell me, because I've just noticed it. Is that 65?
75.
Yeah. Now, do you know, I would have found out later on that that was a mistake, because when you do these, shouldn't you add them up and check that they add up to 1? And if I'd used the 65 number, I would have added them up and I'd say, uh-oh, it's not 1. I better check my I better check my math, right? So I would have eventually figured it out. I didn't figure it out until I did the second one. And lastly, you get 2 right-handed people. And this is going to be a 15 out of 20 times a 14 out of 19. Yikes, that's a number I'm not even going to attempt to guess. 15 times 40 is 210 out of 380. Okay, so I'm going to use these guys to figure out what goes here. Okay, let's do this one. We know the answer is 20 out of 380, which if you do a quick divide top and bottom by 20, you get 1/19. And so I'm going to put 1/19 there. I'm going to skip this middle one for a minute and I'm going to go to the 2 right-handed. The 2 right-handed one was 210 out of 380, which I believe is what, 21/38. Can't do much better, so that's what I've got. And what about 1 right-handed? Well, actually, doesn't that encompass 2 situations? So for that middle one, when I add these 2 together, and that ends up being 150 out of 380, and that's 15 out of 38. And now I'm going to do my check. These 3 better add up to 1. 1/19 plus 15 38 plus 21/38. Fingers crossed. Am I good or am I good? Now, remember that 65 that I had here and the other 65 that I had here? Remember the mistakes I made? If I went and used them as if they were correct, I would have had 1/9. That wouldn't have been 150, that would have been 130. And then I'd finish with 21/38. And you see, I would have went, that ain't 1. Actually, I think I hit the wrong button there, but it still wouldn't have worked. Have you noticed the nuances on these kind of pictures? That you can get one where the sample space you can basically, it's small enough to create, and you make the assumption that everybody is equally likely, and it's pretty straightforward. And then you get the, I'm having 4 children, or I'll stop when I get a boy, which is this kind of probability distribution. And then I've got picking 2 people and a left and a right-handed one. And that's what I got from that one. Are we good? So let's do a question where you've already been given the probability distribution. That'll be the last question for today. So X is going to be the total for 2 dice. And the probability that it happens. So you can get a probability that it's a 2, the total's a 3, 4, 5, 6, 7, and 8, and 9, 10, 11, and finally a 12. Now, if you throw 2 dice, there are 36 possibilities, and in some of the homework questions, didn't they draw pretty pictures of them and you could see what they were? But you're just going to trust me on this, that there's 1 out of 36 ways of getting that. There's 2 out of 36 ways of getting that. There are 3 out of 36 ways of getting those totals. There are 4 out of 36 ways of getting those totals. There is 5 out of 36 ways of getting those totals. And then you've got 636 ways of doing that. Now, I could have simplified those fractions, but actually, if you leave them as 36, do you notice that there's quite an interesting pattern in the answer? And if you drew, you know, it's a big table like that, did you notice that when you got totals, it was diagonals that always added up to the same amount? So if you get a question like that, I can ask questions now like this. What's the probability that you roll 2 dice and it's an even total? Well, all I need to do is look through the probability distribution and pick the ones that represent even totals. Now, before I do this, do you think the answer is going to be a half, 50%? Or do you think it might favour even totals more or less than odd totals? What's your gut feeling? 50%? Or one is more likely than the other? Okay. Even if you haven't shared it with me, hopefully you've got your own idea. So I'm going to use that one, right? That adds up to 4. That one adds up to 2, sorry. That one adds up to 4, 6, 8, 10, and 12. So that's 1, 2, 3, 4, 5, 6 things. 1, 2, 3, 4. There are only 5 things where odd totals happen, but there's 6 things with even. That might make a difference. So I don't have to keep writing lots of 36s. Can I just share a 36 and just add the top? So that happens 1 way, that happens 3 ways, that happens 5 ways, that happens 5 ways, that happens 3 ways, and that happens 1 way. So let's see what that adds up to. 4, 9, 9 and 9. If you roll 2 dice, it's just as likely that the total will add up to an even number, right, 4 or 6, than it is to add up to an odd number. Now, if you went through it, I don't have time, but can you imagine we counted all the ways you could get an odd total, like a total of 3 and a total of 5? That would also add up to 18 out of 36, and that would be a half. Does that seem what you gut feeling was? That it should be probably even? Or is it maybe a surprise to you? You thought it might be more even than odd? Kind of interesting. And we should finish with a joke today, shouldn't we?